Hi Year 9 students, I'm Norman Wildberger. In our last few videos we've been talking about index laws and powers of numbers. Today we're going to extend that discussion by including not just powers of 2 and powers of 10, but thinking about other powers as well. And we're going to enlarge the kind of arithmetic that we're doing with these things, and I'm going to introduce one more index law. Alright, so let me remind you, we're talking about powers, which are expressions like this, say 2 to the minus 5. And I remind you that this number 2 is called the base, and the number up here, minus 5, is called the exponent, or sometimes the index. And I remind you, by the way, that 2 to the minus 5 means 1 over 2 to the 5. You can take that as the definition of 2 to the minus 5 if you like. And 1 over 2 to the 5th is 1 over 32. Alright, so the first thing that I want to do is I want to get you a little bit familiar with powers of numbers whose base is not 2 or 10, the examples that we've been working with so far. So let's start with base 3. Let's think about powers of 3. And I'm presenting some of these powers in a table so you can kind of see the pattern perhaps a little more clearly. In this table, the first row is an integer n. 0, 1, 2, 3 in that direction, minus 1, minus 2, minus 3 in this direction. And below it we have the number 3 to the n. So for example, under 1 we have 3 to the 1, which is 3. Here we see 3 squared, which is 9. Here is 3 cubed, which is 3 times 3 times 3, which is 27. 3 to the 4th is 81. Each time we go up, we are multiplying by 3. So if we wanted to find 3 to the 5th, we would go up in this direction, multiply 81 by 3, which would happen to be 243. Conversely, if we go in this direction, we're dividing by 3. That makes it kind of obvious that this entry here should be 1, which corresponds to what we've seen with powers of 10. So 3 to the 0 is 1. If we divide by 3 again, 3 to the minus 1 is 1/3, 3 to the minus 2 is 1/9, 3 to the minus 3 is 1/27, and so on. So we see that there's some pleasant symmetry. That's very much like this. There's 3 to the 1, and there's 3 to the minus 1. They're reciprocals. There's 3 squared, there's 3 to the minus 2. They're reciprocals. There's 3 cubed, there's 3 to the minus 3. They're reciprocals. Right? So powers of 3. Of course, we could extend by going to more negative integers or bigger integers as well. How about powers of 5? Same kind of table. We can read 5 to the 1 is 5. 5 squared is 25. 5 cubed is 125. 5 to the 4th is 625. So we obtain these numbers by starting with, say, 5 and multiplying by 5 each time. In the other direction, we divide by 5. So that 5 to the 0 is 1. In fact, anything to the 0 is 1. Okay? That doesn't matter what the power is. If you have an exponent of 0, the answer is 1. Carrying on, dividing by 5. 5 to the minus 1 is 1/5. 5 to the minus 2 is 1/25, and so on. And again, there's a symmetry between 5 to the 1 and 5 to the minus 1. They're reciprocals. 5 squared and 5 to the minus 2 are reciprocals, and so on. And here's powers of 4. 4 to the 1 is 4. 4 squared is 16. 4 cubed is 64. 4 to the 4th is 256. 4 to the 0 is 1, just as always. And then here are the negative powers, which are the reciprocals of the positive powers. Now if these numbers look familiar, it's no surprise because the powers of 4 are closely connected with powers of 2. And the reason is because of one of our index laws, our second index law. Remember that 4 is 2 squared. So if we have 4 to the n, that's the same as 2 squared to the n. And the second index law tells us that that's the same as 2 to the 2 times n, or 2n. So every power of 4 is also a power of 2, where the exponent is twice as much as it is for the 4. So for example, 4 to the 5th, which would be the next one in this table, is the same as 2 to the 10. And I hope you remember that 2 to the 10 is 1024, which does agree with this. If you multiply 256 by 4, you would get 1024. Now it's also possible for us to take powers of a fraction, or in fact powers of a negative number as well. The pattern is really the same thing. Let's have a look at powers of a half. So we're talking about a half, and then 1/2 squared, which is a quarter, 1/2 cubed, which is 1/8, 1/2 to the 4th, which is 1/16, and so on. 1/2 to the 0 is still 1. Now 1/2 to the -1 will be 1 over 1/2 to the 1. In other words, 1 over 1/2, which is 2. 1/2 to the -2, for example down here, is 1 over 1/2 squared. That's the relation. 1/2 squared is a quarter, and 1 over a quarter is 4 over 1. You get that by multiplying by the reciprocal of the denominator. 4 over 1 is the same as 4. That's why there's a 4 there. And powers of -1 are very simple, because -1 to the 1 is -1, and then you square it, you get 1. And you multiply by -1 again, you get -1, and then 1. So they alternate -1 plus 1 minus 1 plus 1. And the pattern carries on even for negative integers. So the rule is that -1 to the n is 1 if n is an even number. 0, 2, 4, -2, -4. And it's -1 if n is an odd number, like 1, 3, 5, -1, -3, and so on. Alright, so I want to take us now through some practice problems, where I'm going to show you how to solve explicit examples. Alright, so this will allow us a chance to practice and review and solidify our understanding of these various concepts we've been talking about. So, question 1, evaluate using index laws. Alright, so the first one is 3 cubed times 3 squared. There it is right there. 3 cubed times 3 squared. We use our index law. This is 3 to the 5, because 3 plus 2, the sum of the exponents is 5. And what is 3 to the 5th? Well, it's 243. Remember that table of powers of 3, we went up to 3 to the 4th, which was 81, or 9 times 9. And 3 to the 5th will be 3 times that. 3 times 81 is 243. Next one, 4 cubed all squared. Well, according to the index laws, 4 cubed squared is 4 to the 3 times 2. We multiply the exponents when one exponent is raised to another exponent. So we get 4 to the 6. What's 4 to the 6? Well, we could use our calculator, okay? But if we didn't want to use our calculator, we could think back to our example in the previous slide where I told you that 4 to the 5th was the same as 2 to the 10, which was 1024. So if 4 to the 5th is 1024, then 4 to the 6th is going to be 4 times that. 4 times 1024 is 4096. How about 5 squared divided by 5 to the 4th? This is an example of the third index law. We have one power divided by another power. The law says to take 5 to the 2 minus 4, the difference between the exponents. Well, 2 minus 4 is minus 2. So this is 5 to the minus 2. What is that? That's 1 over 5 squared. In other words, 1/25. So to summarize, here are the general index laws that we're using. These are just a little bit more general formulas that we've already seen in the case of n equals 2 and n equals 10. But they apply for any base n. So n to the a times n to the b is n to the a plus b. N to the a all to the b is n to the a times b. And n to the a divided by n to the b equals n to the a minus b. So notice that in each of these three index laws, the bases are always the same. They're always base n. Whether the base is 3, or the base is 4, or the base is 5, in any one situation, we're sticking with the same base throughout the problem. So these are general index laws that are valid for exactly the same reasons that they're valid when n is 2 and n is 10 that we've already looked at. So just natural generalization of the same situation that we're already familiar with. All right, some more practice problems. Let's evaluate 2 to the 5th times 2 to the 4th divided by 2 to the 6th. So what we want to do in this kind of problem is we want to use the index laws as much as possible to simplify things before we actually have to make any computation. What we don't want to do is get out our calculator and calculate 2 to the 5th, calculate 2 to the 4th, make that multiplication, and then calculate 2 to the 6th and then divide this by this. We want to use the index law to simplify the whole expression as much as we can, and then if necessary at the end, either make a computation on pen and paper, or if the numbers are big, to use our calculator. All right, so how do we use the index laws? 2 to the 5th times 2 to the 4th divided by 2 to the 6th. Well, in the numerator, we have 2 to the 5th times 2 to the 4th. That's 2 to the 9th. So we have 2 to the 9th over 2 to the 6th. That's a quotient, or a division. The bases are 2. So our third index law says that that's 2 to the 9 minus 6. This exponent minus this exponent, which is 2 cubed, which is 8. Next problem, 3 cubed times 3 squared over 3 to the 7. Same kind of thing, except now the base is 3. 3 cubed times 3 squared is 3 to the 5th, because we add the exponents. And then we have 3 to the 5th divided by 3 to the 7, which is 3 to the 5 minus 7. All right, 5 minus 7 is minus 2. So we have 3 to the minus 2, which is 1 over 3 squared, which is 1/9. This is actually a very nice solution to write it out this way, because somebody reading this can see at every stage what steps we're making. Right? Our thinking is clearly presented here. The third problem, 5 to the minus 2 times 5 to the 7, all divided by 5 cubed times 5 to the minus 1. Okay, there's a common base of 5, so we're working with base 5. The natural thing might be to simplify the numerator and then simplify the denominator first using the index laws. So 5 to the minus 2 times 5 to the 7 is 5 to the minus 2 plus 7. We add the exponent when we're multiplying the powers. And in the denominator, same kind of thing. This is 5 to the 3 plus minus 1. The exponents are 3 and minus 1. We have to add them. Simplifying, the minus 2 plus 7 is 5. And in the denominator, the exponent 3 plus minus 1 is a total of 2. So now we have 5 to the 5th over 5 squared. We've simplified it considerably. We can still use the index law because now this is a power divided by another power. So the third index law says that that's 5 to the 5 minus 2. This exponent minus this exponent, which is 5 cubed. And hopefully we can remember that 5 cubed is 125. And if we can't remember it, well, 5 times 5 times 5. 5 times 5 is 25. So we have to multiply 25 by 5. And if necessary, you can do that on the margin. 5 times 25 is 125. All right, so I hope that you can follow the argument. And I hope you can see the advantage in writing things out this way so that a year later, if we come back and look at it, we can see what the argument is. We can see the various steps involved. Yes, from this step to that step, very clear. From this step to that step, very clear, and so on. So if you can express yourself that way, that's what mathematics is about. It's teaching us to express ourselves clearly and concisely and correctly. The 3 C's. Very important. Now, inevitably, when we do mathematics, we practice certain kinds of problems, but often we're asked in an actual situation to put things together in a way that's maybe going a little bit beyond the problems we've practiced with. That's why it's really important to have an understanding of what's going on and not rely on rote memorization. If we have an understanding of what's going on, we can say, all right, this is a bit of a novel situation, but I could just use what I know to go step by step and logically work towards a solution. All right, so here's some examples of that. So this is a problem involving some basically still index laws, but maybe with a bit of additional thinking required. Let's have a look. First problem, 2 cubed times 2 to the 5th times 2 to the minus 4. Well, all right, this is really the same as the first index law, except that we have to do it twice. So when we multiply 3 powers of 2, the exponents are all going to add. We're going to get 2 to the 3 plus 5 minus 4. You can think about that in 2 steps if you like. You could say, well, this product here is going to be 2 to the 3 plus 5. And then when we take 2 to the 8 times 2 to the minus 4, we're going to get 2 to the 8 minus 4. So we get 2 to the 4th altogether. 3 plus 5 minus 4 is 2 to the 4th, which is 16, right? Yes. Next question, 4 cubed times 2 to the 5th. Do we just add the exponents? No, it's not so simple because the bases here are not the same. Here there's a base of 4. Here there's a base of 2. We can only use that first index law when the bases are the same in the 2 powers that we're multiplying by. So they're not the same here, so we have to think about how we're going to convert this into a situation where they are the same. And the observation that's the key one is that this number 4 is actually a power of 2. So with just a little bit of work, we can convert this into a question that has bases of 2 all the way through. So how do we do that? Well, we just write that 4 is 2 squared. We just replace this 4 with a 2 squared. So now we'll have 2 squared all cubed times 2 to the 5th. How can we simplify that? Well, our second index law tells us what to do with this. 2 squared all cubed is 2 to the 6. Because 2 times 3 is 6. So this equals 2 to the 6 times 2 to the 5. And now we're in a position where the bases are the same. That's much simpler. We just add the exponents now to get 2 to the 11. And what is 2 to the 11? Do we need our calculator for that? Well, that's still in the range of computability for us because we happen to know what 2 to the 10 is. You see, 2 to the 11 is 2 to the 10 times 2 to the 1, or just times 2. We know that 2 to the 10 is 1024, so we just have to multiply that by 2, and we'll get 2 to the 11. There it is right there, 2048. All right, and the third question, 3 to the 4th times 9 to the minus 1 divided by 9 squared. There it is again. Well, we're in the same kind of situation as we were up here. We have base 3 here, but here we have base 9 and base 9. To simplify things, we want to convert everything to the same base. Then we can use the index laws that we're familiar with. What base are we going to choose? We should choose the base 3, because 9 can be expressed as 3 squared. So we can rewrite this as 3 to the 4th times 3 squared to the minus 1 divided by 3 squared squared. You see, we're replacing the 9 here and here with 3 squared. Now we have to simplify this, and we can do that because we know that 3 squared to the minus 1 is 3 to the minus 2. This is an exponent to an exponent, so the result is to multiply the exponents. 2 times minus 1 is minus 2. And in the bottom here, we have 3 squared all squared. That's 3 to the 4th. Again, it's a question of multiplying this 2 times that 2. All right, so at this stage here, there is a little observation we can make to simplify things. We see that this 3 to the 4th in the numerator is matched by a 3 to the 4th in the denominator. Remember, whenever we have a quotient, we can divide the top and bottom by the same amount, and nothing's going to change. So we can cancel the 3 to the 4th here and the 3 to the 4th there, leaving just a 1 on the bottom and a 1 up here at the top. So we cancel the 3 to the 4ths and we just get 3 to the minus 2. What is 3 to the minus 2? It's 1 over 3 squared, which is 1/9. All right, so we've looked at a couple of examples here. Please go over these if necessary. Easy to rewind the video, have a look at each question, and follow the arguments. See that you understand things step by step. We're basically using the same laws that we're already familiar with and going a little bit further. So our understanding of these index laws is being augmented here and solidified. All right, so finally, I want to introduce one more index law. And this index law, the fourth one, is a little bit different from the previous ones because it combines the idea of having two different bases going on at the same time. So here's the law in the general form. It says m times n to the a is m to the a times n to the a. For example, specific example which makes it a little bit clearer, perhaps easier to understand. 2 times 3 to the 4th is 2 to the 4th times 3 to the 4th. That's a special case when m is 2, n is 3, and the exponent a here is 4. So why is this law valid? Let's have a look at it in this special case here, which illustrates why it's true in general. Let's have a look at the left-hand side. 2 times 3 to the 4th. What does that mean? What does it mean to take something to the 4th power? It means you take that something and you multiply it by itself 4 times. In this case, 2 times 3 times 2 times 3 times 2 times 3 times 2 times 3. That's what 2 times 3 to the 4th means. All right, now we look at this and say, all right, can we rearrange this? There's all these multiplications going on. And with multiplications, there are two important laws. There's the associative law. It doesn't matter in what order you bracket things. So we can remove all the brackets. And the other important law is the commutative law. That 3 times 4 is the same as 4 times 3. that 5 times 8 is the same as 8 times 5. So we can interchange the orders of any products. In particular, we can take all these 2's here, there are 4 of them, and bring them all together. And then take all the 3's and bring them all together. So there are going to be 4 2's, 1, 2, 3, 4, and there are going to be, of course, 4 3's, 1, 2, 3, 4. When we rewrite things this way, we see that this expression is just 2 to the 4th. And this expression is just 3 to the 4th. So that's why 2 times 3 to the 4th is 2 to the 4th times 3 to the 4th. And the same argument really applies in general. So for example, suppose we want to calculate 4 times 3 to the minus 2. Alright, 4 times 3 is 12. But suppose for some reason we forgot what powers of 12 were. We were nervous about powers of 12. What is 12 squared? We can't remember. Well, we could apply this law. This is 4 times 3 to the minus 2. So according to the law, this is 4 to the minus 2 times 3 to the minus 2. These numbers are a little bit smaller and more manageable. 4 to the minus 2 is 1 over 4 squared, or 1 over 16. 3 to the minus 2 is 1 over 3 squared, or 1 over 9. And then once we have 1 over 16 times 1 over 9, we can do the multiplication and get 1 over 144. That's an illustration of this fourth index law. Alright, so very good. We've done a lot of work with index laws. We've seen different bases at work today. And we've combining different bases, and we're doing a little bit more sophisticated arithmetic than we were doing previously. Time for some practice problems. Alright, so our first problem is to evaluate certain expressions where index laws are naturally involved. And the strategy I want you to adopt is to try to use the index laws to simplify things as much as possible until you just have one power to evaluate pretty well at the end. And then if necessary, you can use your calculator if that power is a very large one, if you can't calculate it by hand. But if you can calculate it by hand, I much prefer that you do that. Alright, so 3 squared times 3 to the 5th, 7 squared times 7 cubed divided by 7 to the 4th, 4 divided by 4 cubed times 4 squared, 5 squared times 5 squared, 3 to the 4th divided by 9, and 4 to the 5th divided by 2 to the 7th times 4. And there's the solutions in some order. And the second question, evaluate these expressions. 3 to the minus 1 times 3 to the minus 4 divided by 3. 5 squared divided by 5 cubed divided by 5 divided by 5 to the 4th. 8 times 2 to the 0 divided by 2 to the minus 3. 6 to the 4th divided by 2 squared times 3. 2 times 7 squared. And 2 cubed times 3 to the 5th times 7 squared divided by 2 squared times 3 to the 4th times 7 cubed. There are some answers. Alright, so these are rather varied problems. I'm not giving you a lot of problems which are very similar to each other. If this was a class, I would probably do that. Right? So if I was actually running a course, I would be giving you a lot more problems to do. And there would be a lot more that would be sort of similar to each other. But in this video situation, I don't have time, and I don't want to strain your patience too much by giving you a lot of problems which are very similar to each other. Right? So these problems really represent sort of the final understanding that I want you to have. Okay, I want you to think about things, and these are problems that may require some careful thinking, going over previous examples, having a look, thinking about what's going on, and sort of seeing if you can really understand things to be able to work through them and get the answers. If you can get the answers, you're doing really, really well. Okay, you're making really good progress, and your understanding of index laws is now at a very good stage. In our next video, we are going to apply index laws to something a little bit different, to scientific notation. This is a way of systematically expressing very big numbers and very small numbers, which is used by scientists, by physicists, chemists, engineers, in practical working situations. So it's actually quite an important tool that we can get at by using our index law understandings. So I hope you'll join me for that. I'm Norman Wildberger, and we'll see you all next time.